Hello viewers and welcome to another episode of Space Science with Python. Today we will code a little bit around the dwarf planet Ceres. Now last time we had a concept video where I was introducing you the fundaments of orbital elements, and today I would like to dive a little bit deeper into this topic by computing the orbital elements of an actual object, namely Ceres. So we will not really make any larger predictions or so. We will use some spice kernels, we will compute some state vectors and convert the state vector into some orbital elements to see what kind of functionalities we have in spice to compute these values. Now a quick picture of the object of interest. So this is Ceres. It was discovered over 200 years ago, the very first dwarf planet in our solar system by Giuseppe Piazzi, and was also visited by the Dawn mission, the mission from NASA that visited the dwarf planets Vesta and Ceres, and I think Ceres was visited around 6 to 5 years ago. So this is an actual image of this, but we will not talk about images, but now more about the orbital elements. And for this, we have a new folder in our GitHub repository, namely Ceres. And also there is a Jupyter notebook where I just already prepared 2 small cells, and also a kernel meta file with some spice kernels. And there are also 2 new spice kernels in the repository that we will cover today. Now, what do we want to do? Well, first we want to compute the state vector of Ceres for any given time, and then based on the state vector we can recompute or derive the orbital elements. And based on the state vector, and of course based on the orbital elements, we can also again compute some state vectors. This is a little bit like computing in a loop, because we have the kernels, but with the kernels we can verify our computations using the orbital elements and see whether it makes sense or not. Now for Ceres we need new spice kernels. So the spice kernels we used for now were only suitable for the planets, so it only contained the major inner planets, and today we need to download new kernels. And for this we go again to our NIF kernel repository. The link is provided in the description. And there we scroll down to generic kernels, and we want to compute something with positions, so state vectors and so on. So we need the so-called SPK kernels. So let's click here, and there we click on asteroids. So I know it's dwarf planets, but Ceres, Vesta, and its cousins are all stored in the asteroid section. And there we have some text files, some kernel files, and we can take a look into the AA readme txt as always, and there we find some information what's in the repository. There's also another AA readme in there that explains us a little bit which objects are covered in the repository, in the kernels. And there we see in the very top Ceres, the very first dwarf planets with the NIF code with respect to the Sun in the interval of 1800 or 1799 to almost 200 years from now. So covering in total around 400 years. So we have also other dwarf planets like, for example, Eros, as well as Cleopatra, or also Lutetia or Vesta. But for today, we will stick with Ceres. Now let's go back. So we need this kernel, the BSP kernel, around 60 megabyte of size. It's a little bit large for to add this in a GitHub repository, but I just did it, so you don't have to be bothered by downloading it manually or so. So I hope GitHub allows me this. Of course, there's something like GitHub LFS for larger files, but as long as GitHub is not complaining, I will just take it. The second file also here, a TF file, and this text file contains also the codes, for example, Like for example, here the Ceres and the corresponding NIF number, and also some definition of some reference frame. So we know the ecliptic J2000 reference frame, which is the ecliptic coordinate system that we talked about a few weeks ago. But here it's a new frame. It's called ecliptic J2000 DE408 frame. Now the definition is here, but let's not take a look here, but let's talk more about what is this frame about. And maybe you recall this DE405, these kind of kernels were used also in the NASA Horizon system. So in the NASA Horizon system, these kernels are mostly displayed, and yeah, let's not reverse engineer the definition that is shown here, but we can use some functionalities in Spice, in Python, to see whether there is a difference between the, let's say, standard ecliptic J2000 and this ecliptic J2000 DE405 frame. Now in the Python code, we have now two cells. The one is importing some modules, and the second, as the other scripts, is loading some kernel and computing the UTC date time for now, and is also converting it already to ephemeris time using the Spice function UTC to ET. Now, before we compute any state vectors, we can check whether this this ecliptic J2000 DE405 reference frame is somehow something else as the standard ecliptic J2000 reference frame. So we can define a matrix. Before I do this, maybe let's run the first cells. Yeah, we can define a matrix, transformation matrix, where we use SpicyPy and call the function sxform. And sxform computes the transformation matrix for state vectors from one reference frame to another. So the resulting matrix has a dimensionality of 6. So it's a 6 times 6 matrix that can be applied to some state vector in a given reference frame and then converts it to the output reference frame. And the input reference frame is here now ecliptic J2000 DE405. And the I didn't learn it. I really have to turn off the autofill, autocompletion, and the output string. So the output reference frame is ecliptic J2000, and we have to provide a ephemeris time. So in our case is date time ET, and then we can simply print out the matrix to see how it looks like. And this is our result. And we see, now this is not well formatted. We should maybe print it, for example, row by row to make it more user-friendly or more friendly for the eye. Metro. Maybe we should also round the values by 2 digits to make it even more readable. I did a mistake. There is a dot. Yeah. So let's see. We have a matrix that's, the unit matrix, no, identity matrix. We see here ones in the diagonal. We have here, okay, -0, so it's probably a very, very small value, something like 10 to the power of -17 or so. We just saw it in a second ago. So basically, there is no actual difference between ecliptic J2000 DE405 and ecliptic J2000. So yeah, this reference, the values are given in this reference frame, but yeah, it's basically the same as ecliptic J2000. I have to be honest, I don't know why they have it here. You mostly read this DE405 in the NASA Horizon system. Why they have a different naming convention, I'm not sure. Maybe it's some kind of heritage or so reasons. I don't know. Now, in our next step, we can compute the state vector of Ceres. So we create a state vector, and it also returns our so-called light time, but we will use it as an empty. We will not take this variable from the already known function spkgeo. So maybe you recall this function. We want to compute the state vector of an object, of a target, with respect to an observer in a certain reference frame given a certain ephemeris time. Now the target is now the 2 with the several zeros. I think it were like 5 zeros. Yeah, let's see. Maybe hopefully no error will occur. And this is the target, so Ceres. The ephemeris time is again the date time. And then we have also our reference frame, which is Eclipse J2000. And then we have also our observer, the sun. So we can take a look at this. It's just some value given in kilometers and kilometers per second. Not kilometers. And that's the state vector. So we can compare it with NASA Horizon System, but we did this task already once. So let's be sure that this is the correct state vector. Now, if we want to compute orbital elements, we also need the gravitational parameter times the mass of our sun, and we also know the function for this parameter. So I call it now, something like the GM sun pre-value, because the value, this output here is an array, not a float. And we use the function bot VCD. The body ID is 10. We want to have the item G times M. And the maximum dimensionality, or the dimensionality of the output, is 1. So if you, for example, return the radii of an object, is of course 3. So this value is in 3-dimensional. And this number here, or the first output, is the dimensionality of our output. So to get the G time, the gravitational parameter times the constant, times the mass of the sun, we have to take this value and just assign the entry of the array, and then we get the float. So let's take a look. GM times the sun. Yeah, that's basically it. Okay, cool. Now we can compute the orbital elements of Ceres. So we can say Ceres orbital elements equals to spicypi dot oscald x. So oscald x is now a new function we introduced today, and this function takes the state vector of a certain object. It takes the corresponding ephemeris time, and it takes the gravitational parameter times the mass of the central body to compute the orbital elements of the object with the given state vector for this particular time. So we use the spice kernel that provides the information, the state vectors, to compute the current orbital elements of the body. Now you may say, well, this should theoretically be independent of the time, and theoretically you're right. But if you have some more sophisticated computations where you consider, for example, the gravitational perturbations of an object. So, for example, Jupiter has a large gravitational pull, Saturn, or basically also the other planets. Then the orbital elements, they change all the time. Only slightly. Some other objects change. Their orbits change severely. For some certain comet types, we will take a look at this in a future video. But Ceres should be more or less, be rather stable, let's say. So let's compute the value. We have oscald x. We take the state vector that we just computed, Ceres state vector. We have the ephemeris time. Oh, this was the caps lock. Ephemeris time is equal to date time et. And then we have also the gravitational constant times the mass of the Sun. And this returns us a set of orbital elements. Now, the orbital elements, we can just take a look at this array, and you see there are a lot of parameters. And yeah, let's not go here step by step through it, but really computing it here in this cell. So maybe you remember the last video I showed you, the concept video about orbital elements. So, and these orbital elements, they are in this resulting array. So we can just extract them, and we convert it also because all these values are given in kilometers, and let's have it in a more readable format, namely AU, degrees, and so on, because the values are given in kilometers and radians. And the 10th value, I think this should also be the last one, not 100% sure, is given in kilometers, and we want to have it in astronomical units. And this one is the semi-major axis, now given in AU. We have also the perihelion. We can also convert it to AU, and this is the very first entry of our array. Now we have also the eccentricity of Ceres. I can just copy paste it here. And in this case, it's the second, or the, let's say, index 1 entry. Now we have also the inclination. It's given in radians, so let's convert it to degrees. And in this case, it's the next one. So this is now the inclination of Ceres. I can now, let's copy paste it. The longitude of ascending node is the next one. And maybe you already have a feeling for orbital elements, what is missing. The argument of periapsis, or the argument of perihelion, and this is this value. And the values in between, yeah, let's ignore them for a moment. We can now also compute the orbit time, the Ceres orb time in years. And in this case, it's the 10th element, but it's given in seconds. So we have to divide it by, of course, 365 days times the number of seconds per day. So 86,400 seconds. Yeah, so this is basically it. Now, before I execute this command, we can also say, okay, we want to print all the values. Now, here I do it now, let's say, quick and dirty. In our in the Jupyter notebook that I provide in GitHub, everything is, of course, formatted properly. So let's make a quick print. Now we have the eccentricity, we have the inclination. Of course, using some f-string would be, of course, better to make it more readable, but again, here in the video, you can just do it quickly, and later, if you want to do some recap, just take your time and go through it step by step. Of course, we can compare these values with some kind of reference, and I will show you the reference in a moment. But first, let's compute these values. And here are our results. Now, we can compare these values with the values from the so-called Minor Planet Center. The link is also provided in the description. And the Minor Planet Center provides also some data for minor planets, as the name suggests, indicates. And here for the dwarf planets, we have Ceres with all the different parameters. The first parameter we extracted was the semi-major axis, so the small a. Here it's given as 2.77. In our case, is 2.7, 7 if you round it up. So of course, this number here suggests a precision we don't actually have. We have to consider also the error or the uncertainty, but we don't have it here now. The next value is the perihelion, let's say 2.55. And here it's a Q, it's 2.55. Well, also quite good. Eccentricity is 0.07008. Eccentricity here, 0.8, perfect. The next one is the inclination with 10.59 degrees. Inclination here, okay, it's now rounded up to 10.6, so this checks out. Then in the next one would be the longitude of ascending node and the argument of periapsis. And here the argument of ascending node is this small value here. It's 80.3 and argument of periapsis is 73.7. And here we have 80.3 and 37.7. So this looks good. And the last one is, of course, the orbit time in years. Of course, I didn't, actually it's 365.25 years and so on, I know, but just quick and dirty, 4.6 years. And here we have P, the period in years, it's 4.6 as well. Now we don't dive in too much into the other values, but we see that with the spice kernel that we downloaded provides state vectors that if we reconstruct the orbital elements, we get, let's say, believable results. And this is quite nice. Of course, based on the orbital elements, we can also now compute the state vector. So for example, we don't have always spice kernels for everything. So having a spice kernel for a particular object or other objects of interest is quite a luxury, because NASA or ESA, they do not provide kernels for all objects. So, but we have, for example, 20,000 near-Earth objects. We have hundreds of thousands of asteroids in the main belt and other objects out there. So only for the major one, they provide kernels. For the rest one, we have, let's say, to deal only with the orbital elements. And if we only have orbital elements, we can still compute the state vector. And for this, SPICE provides us a new function, which is called conics. And conics requires two inputs. First, an array with orbital elements and the gravitational constant times the mass of the larger central body, in our case again the Sun, and the corresponding ephemeris time to compute the position of the object. Now here in our case it's quite simple. We already have the orbital elements. So what does it require? We can maybe take a quick look. Didn't prepare it now, but let's go for some quick research. NIF conics, SPICE conics. So it requires conical element as an input, so this is the documentation, and it requires the perifocal distance, the eccentricity, inclination, longitude of ascending node, argument of periapsis, the mean anomaly at epoch, the epoch, okay, we talk about it at some other time, and the gravitational parameter. And the nice thing is that this input structure is the same structure as has been provided by the Osgeld X function. So what we simply can do is we can just say, okay, we take the first entry, we take now second entry, take this one, third, and this goes for 7 parameters now. Didn't mean to do this. Fourth one. Of course, this can be done way easier, I know, just for demonstration purposes, to really underline the simplicity of the format of Spice that is being used as an output and input. So Spice is very convenient. It doesn't change output formats or so between different functions. So it's very convenient to use. And of course now here GM times the sun. And then we have also, I think I have a, yeah, this is too much. The date time ET. And what we can do now is we can first print the state vector from the kernel, so the one we computed here already. And now we can do the same thing with the state vector that is being computed based on the orbital elements. So let's use this one again. And you see the values are identical. So we have now, we can, if we don't have any Spice function, Spice kernel, we can simply search for the orbital elements and compute the state vector of an object using the orbital elements and the corresponding ephemeris time. And this all does not apply for the sun. We can also compute, the orbital elements of the moon around the Earth or the other moons around other planets and so on. So, summary, what did we learn today? Now, today we learned that Spice has a lot of, or NASA provides a lot of different kernels, also for the dwarf planets. And we computed the orbital elements, or the state vector first, and then based on the state vector, we computed the orbital elements from the state vector. We compared the orbital elements with some reference from Minor Planet Center, and we saw that it makes sense. And based on the orbital elements, we computed this state vector again. So not using the Spice kernel, but using the orbital elements. We saw that we were able to reproduce our results. And now we are able to compute any state vector of any object where we have the orbital elements given. And this will be very useful in the future for future videos. So I hope you liked the video and the coding session was not too difficult. Again, the Jupyter Notebook is provided in the GitHub repository. The link is also provided in the description. And until next time, take care everyone and see ya.